Britain entered the late 1930s with a global trading economy dependent on sea lanes and a defense establishment shaped by post-1918 retrenchment. The Royal Navy still maintained worldwide stations and treaty-limited tonnage, but many capital ships were built before 1921 and required modernization. The merchant fleet measured roughly 17 to 18 million gross registered tons in 1939, carrying the bulk of food, fuel, and raw materials that could not be sourced domestically. The geographic position of the British Isles imposed a strategic constant. Any major war would be a contest of shipping protection, industrial throughput, and access to overseas inputs. Policymakers framed rearmament around those constraints, balancing treasury limits with the need to reconstitute capacity for naval construction, aircraft production, and emerging technologies such as radio detection. Interwar treaties fixed naval ratios among the principal powers while encouraging qualitative improvements. Britain maintained treaty levels comparable to the United States and above Germany, which was restricted by Versailles until the 1935 Anglo-German Naval Agreement. By 1939, Germany had built modern cruisers, destroyers, and U-boats, but fewer capital ships than Britain. Italy concentrated on the Mediterranean balance. Japan emphasized fast carriers and battleships in the Pacific. British planning assumed a two-ocean security obligation that could be strained by simultaneous crises. This calculus drove investments in escort construction programs, new yards for destroyers and corvettes, and retention of dispersed shipbuilding on the Clyde, Tyne, Mersey, and Belfast to limit vulnerability and preserve skilled labor pools. Air policy turned on the judgment that an air offensive could threaten cities and ports critical to shipping and industry. The Air Ministry launched expansion schemes in the mid-1930s, standardizing airframes such as the Hawker Hurricane and Supermarine Spitfire, and committing to engine families capable of rapid uprating. Rolls-Royce developed the Merlin from a private venture into the principal liquid-cooled engine for fighters and bombers. Bristol advanced sleeve valve radials such as the Hercules. Napier and Armstrong Siddeley pursued high-output designs for specialized roles. To scale output without overwhelming existing plants, the government organized a shadow factory system that placed new workshops adjacent to, or partnered with, automotive and engineering firms in the Midlands and Northwest. By 1939, airframe jigs, heat treatment lines, and test cells were being installed across dispersed sites to mitigate bomb damage risk and to draw on a wider labor base, including women trained through technical colleges and factory schools. Scientific preparedness centered on early warning and fire control. The Committee for the Scientific Survey of Air Defense, convened in 1935 and often associated with the Teasert Group, coordinated laboratories, universities, and industry. Experimental work at Bawdsey and follow-on stations produced operational radio direction, finding along the east and south coasts by 1938 to 1939. The chain home system, integrated with observer corps posts and fighter command control rooms, created a doctrinal shift. Interceptors could be scrambled to altitude only when tracks crossed defined trip lines, conserving pilots, aero-engines, and fuel stocks. Parallel work developed gunnery radar for ships and centimetric research that would later influence anti-submarine warfare and night fighting. These projects required vacuum tube supply chains, precision machining for magnetrons, and standardized test procedures, an industrial as much as a scientific undertaking. At the ministerial level, Whitehall restructured the state's interface with production. The Ministry of Supply was formed in 1939 to coordinate Army equipment and the metallurgical and chemical inputs that cross service boundaries. Admiralty retained control of naval contracts and dockyard workloads, but worked with supply officials on plate, turbine, and armor allocations. In May 1940, a dedicated Ministry of Aircraft Production took over from the Air Ministry's supply directorates, concentrating on throughput, interchangeability of parts, and statistical control of subassemblies. The Treasury, facing gold and dollar constraints amplified by the need to purchase petroleum, bauxite, machine tools, and ball bearings abroad, negotiated credit arrangements and later agreements with the United States and Dominions to sustain procurement without exhausting reserves. The civilian economy adjusted in stages. Before September 1939, unemployment pockets in shipbuilding regions coexisted with new investment in aircraft zones. Labor dilution agreements with trade unions were negotiated to permit broader entry into skilled roles under supervision. After mobilization, reserved occupations kept skilled riveters, platers, pattern makers, tool setters, and test engineers in factories rather than in uniform. Rationing schemes for food and clothing were introduced not only for equity, but to stabilize demand and free transport capacity for strategic goods. Coastal traffic patterns were redesigned to reduce exposure to submarine interdiction, shifting cargoes by rail where possible and concentrating convoys under escort where sea carriage remained essential. Britain's imperial and alliance connections shaped the preconditions for industrial coordination. The dominions and colonies provided iron ore, non-ferrous metals, fuels, timber, and foodstuffs. Canada possessed machine tool and automotive capacity adaptable to aircraft and vehicle contracts. India and African territories supplied raw materials and labor for base construction. Conversely, Britain's commitments to furnish aircraft, vehicles, radar sets, and naval escorts to multiple fronts required careful sequencing. Early war agreements with France integrated certain artillery, aero-engine, and munitions orders. After 1940, arrangements with the United States added new flows of components and capital equipment. The Tizard mission of 1940 transferred technical data, including radar, jet concepts, and ordnance fuses, seeking reciprocal production that British factories alone could not meet at the required scale. Intelligence assessments in 1938 to 1939 estimated that Germany could field large bomber forces and expand U-boat construction, compelling Britain to prioritize fighter output, radar coverage, and escort-class shipbuilding. Public sentiment accepted air raid precautions and blackouts. Evacuation plans moved children and vulnerable populations from port and industrial centers to reduce anticipated casualties and sustain labor reliability. The armed forces mobilized with regulars and reservists. The Royal Navy could crew destroyer and corvette programs, but required rapid training for new escort groups. The Royal Air Force expanded operational squadrons alongside the maintenance and training commands that absorbed engines, spares, and ground equipment. The Army's call-up drew on the same mechanical skills needed in factories, necessitating tighter reserved occupation lists and training pipelines. By the outbreak of war in September 1939, the foundation for total war organization existed but remained incomplete. Shipyards had slipways and turbine shops scheduled for escorts and capital repairs. Yet reliance on imported oil and specialized alloys imposed exposure to maritime interdiction. Aircraft firms held orders for thousands of airframes and engines, but jigging, subcontracting, and quality assurance still varied among plants. Radar chains were operating, but inland coverage and seaborne applications were partial. The preconditions combined strengths, experienced naval constructors, an emerging aviation supply base, a national early warning concept with vulnerabilities, financial reserves under strain, dispersed but uneven industrial tooling, and a logistics architecture reliant on protected shipping. These realities framed Britain's subsequent effort to organize industry for naval construction, radar deployment, and aero-engines while supplying allies across several theaters. War began for Britain on the 3rd of September, 1939, with a sequence of administrative and operational moves that mapped immediate priorities onto industrial realities. Admiralty orders reintroduced convoying on Atlantic routes within days. The first Halifax convoy, HX-1, sailed on the 16th of September, reflecting the calculation that protecting bulk cargoes mattered more than individual voyage speed. Destroyer flotillas were allocated to western approaches, home fleet screening, and channel patrols, creating escort gaps that would be filled by emergency construction. The War Office mobilized the Expeditionary Force for deployment to France. Its logistic demands on ports and railways competed with coal, grain, and petroleum flows. So, shipping plans were adjusted to stage military cargoes through specific harbors and shift civilian imports to alternate routes. The Air Ministry activated fighter, bomber, and coastal commands within a national air defense plan anchored on early warning and controlled interception. Each decision carried direct implications for shipyard berths, engine test cells, and radar installation crews. The command structure evolved quickly. Neville Chamberlain remained Prime Minister until May 10, 1940. Winston Churchill served as First Lord of the Admiralty from September 1939, then became Prime Minister and Minister of Defense in May. At sea, the First Sea Lord and the Admiralty Board directed escort policy, repair priorities, and armament allocations to destroyers, sloops, and auxiliary vessels. Fighter Command under Air Chief Marshal Hugh Dowding managed an integrated system of radar stations, observer corps posts, sector operations rooms, and fighter squadrons. Within the aircraft supply chain, the Air Ministry's production directorates worked with prime contractors and the shadow factories. After May 1940, a separate Ministry of Aircraft Production centralized throughput, tooling, and spares policy. The Ministry of Supply coordinated Army equipment and controlled key materials such as armor plate, copper, and high-speed steel, liaising with the Board of Trade and Treasury on import licensing and exchange usage. Radar entered routine service in the opening months. Chain home stations along the east and south coasts provided long-range warning against high-altitude aircraft, while low-level coverage expanded with mobile and short-range sets. Site preparation required standardized masts, power supplies, and secure landlines to filter rooms. Production of transmitter valves, magnetrons for centimetric research, and precision components was assigned to firms with prior radio expertise, and to general engineering companies after retooling. Coastal radars for navigational aid and gunnery ranging were planned in parallel for fleet units and defended ports. Binding scientific schedules to dockyard refit cycles and contractor yard availability. Naval construction pivoted from capital units already on the slip to escorts and auxiliaries required immediately. Flower-class corvettes were ordered in numbers suitable for smaller commercial yards that could handle simple hull forms with reciprocating machinery. Larger yards concentrated on fleet destroyers, Tribal and J classes under earlier programs, and new anti-submarine destroyers with improved sonar and depth charge capacity. Existing merchant hulls were earmarked for conversion to ocean boarding vessels, auxiliary anti-aircraft ships, and fleet oilers. Refit lists were prioritized to return older destroyers to service with updated sonar and anti-aircraft armament, often replacing single-purpose guns with multiple light weapons, better matched to air attack profiles encountered in coastal waters. Aircraft and engine output accelerated, but had to absorb the bottlenecks of 1939 tooling. Hurricanes and Spitfires drew on different airframe lines, but shared the Merlin family, so decisions on engine variant allocation directly affected squadron readiness. Rolls-Royce increased crankcase machining and supercharger production, while subcontractors took on cylinder blocks, reduction gears, and magnetos. Bristol scaled Hercules radial lines for bombers and coastal aircraft. De Havilland prioritized constant-speed propellers to shorten takeoff runs with heavy loads and improve climb to interception altitude. Training commands expanded flying schools, creating demand for basic trainers, fuel, and spares that competed with frontline units unless carefully scheduled. The Maintenance Command organized depots to receive engines for overhaul on hour limits that varied by mark and setting, balancing reliability against the urgency of keeping squadrons operational. The maritime supply problem defined the opening phase of Britain's role as a supplier to allies, with metropolitan factories concentrated in the Midlands, Lancashire, and the Clyde-Tyne-Mersey Arc. Finished aircraft, engines, and munitions moved by rail to ports selected for convoy assembly. Early deliveries to France included aircraft, vehicles, and ordnance that had to be staged through South Coast ports under air raid precautions. Simultaneously, the government placed orders in Canada for corvettes, minesweepers, and aircraft to broaden the industrial base and hedge against air attack on British plants. Canadian Car and Foundry prepared to build Hurricanes. Shipyards on the St. Lawrence and Great Lakes took standardized escort hulls suited to their dimensions and workforce skills. Coordination with South African and Indian workshops began for repair facilities and spares manufacture, allowing dispersed production of non-critical components and freeing British capacity for engines, optics, and high-grade metallurgy. Operational experience fed back into procurement. The U-boat threat in the western approaches and the air mining of shipping lanes increased the priority of mine-sweeping gear, ASDIC sets, and depth charge throwers. Corvette and sloop designs were modified for better seakeeping and endurance. Air combat over the North Sea and the Channel in late 1939 and early 1940 informed decisions on armament harmonization, gun heating, and reflector sights. Night bombing raids on coastal installations prompted the deployment of searchlight control radars and the development of airborne interception sets, which required compact transmitters, antennas, and specialized operator training. Each technical change translated into new contract schedules, revised jigging, and additional test equipment. Manpower policy in the first months attempted to hold skilled labor in shipyards and engine plants while raising the expeditionary force and home defense units. Reserved occupation rules were expanded. Dilution agreements brought semi-skilled and newly trained workers onto tasks under craft supervision. Technical colleges delivered compressed courses in welding, gauge reading, and engine test procedures calibrated to the needs of specific factories. Women entered inspection, electrical assembly, and instrument work in numbers that rose as factories extended shifts to meet throughput targets. Housing, transport to dispersed factories, and canteen facilities became part of production planning, with local authorities and companies coordinating to maintain attendance and shift stability during blackout conditions. Public administration adjusted to the realities of air and sea threats. Civil defense organizations integrated with industrial security to protect key plants, docks, and power stations. Fuel allocation boards balanced civilian coal and petrol against naval bunker fuel and aviation spirit requirements, moving storage inland and creating pipeline links to reduce coastal exposure. Insurance schemes for war damage and government guarantees for plant investment encouraged contractors to expand facilities. Statistical control offices began to track machine tool utilization, scrap rates, and time on test for engines, establishing baselines that would drive later productivity gains. By the spring of 1940, Britain had completed the initial transition from peace to war production, while confronting simultaneous operational demands in home waters and on the continent. Convoys were routine, escort shortages were being addressed by emergency programs, radar networks were functioning with planned extensions, and aero-engine output was climbing within the limits of tooling and skilled labor. The groundwork for supplying allies was visible in cross-Atlantic orders and Dominion participation, but the system remained sensitive to shipping losses, bombing disruption, and foreign exchange constraints. The opening phase thus established the institutional and industrial mechanisms that would define Britain's total war organization as the conflict widened. Strategic planning in 1939 to 1941 translated broad aims into measurable outputs, route structures, and plant schedules. For Britain, the core objective was to keep import and troop convoys moving while raising aircraft and engine production to levels that could sustain air defense and maritime patrols, then generate surpluses for allies. The Admiralty's planning staff modeled convoy cycles between North America, West Africa, and the British Isles, assigning destroyer and sloop groups to convoy speeds of 8 to 10 knots for bulk cargo and higher for fast liners. The Ministry of Shipping converted these models into berthing plans and bunker allocations, while the railways scheduled inland movement of grain, petroleum, and ores from western ports to industrial regions. The Air Ministry and, after May 1940, the Ministry of Aircraft Production set monthly targets for fighters, coastal aircraft, and engines, linking them to the Shadow Factory system at Castle Bromwich for airframes, Hillington and Crewe for Merlins, and Bristol sites for Hercules radials. Radar deployment plans extended chain home to overlapping arcs with defined maintenance intervals and spares pools, so that station downtime could be forecast like a factory overhaul. Across the Channel, German planners pursued a commerce war designed to reduce Britain's import capacity below subsistence. Admiral Karl Dönitz argued that approximately 300 ocean-going submarines operating in coordinated groups could overcome escorts on the western approaches. In September 1939, Germany had several dozen ocean-going U-boats available for sustained operations and aimed to expand rapidly. Surface raiders and mine layers were tasked to add pressure on convoy routes and port roadsteads. The Luftwaffe prepared to attack docks, storage tanks, and industrial districts, with air mining of approaches as a force multiplier. Italian planning in 1940 sought to contest the Mediterranean with submarines, torpedo boats, and bombers, aiming to sever the Suez route and force British traffic around the Cape. Japanese force development was not yet committed to war against Britain, but British planners treated the Far East as a constraint, maintaining Singapore's strategy on paper and apportioning limited modern units to the Indian Ocean when shipping allowed. British procurement objectives had to reconcile currency limits with physical capacity. Treasury and Board of Trade officials set dollar budgets for machine tools, high-octane fuel components, and ball bearings, while the Ministry of Supply prioritized armor plate, copper, and alloy steels across services. Contracts were standardized to shorten negotiation time. Escort construction was pushed into smaller commercial yards via a program of Flower-class corvettes that used reciprocating engines and commercial practices. Larger yards took Hunt-class destroyers and fleet destroyer programs already in train. Dockyards and contractor yards coordinated refit cycles to add ASDIC, additional depth charge stowage, and light anti-aircraft armament. The aim was not only numerical growth, but configuration convergence, so that spares and training could be rationalized. Aircraft planning moved from airframe counts to engine and propeller bottlenecks. Fighter command required an expanding pipeline of Merlin engines with uniform mountings and controls. Bomber and coastal commands needed Hercules radials in marks appropriate to operational altitudes and fuel grades. Rotol and de Havilland scaled constant-speed propellers to reduce takeoff distance and improve climb, which had to be reflected in training syllabi and maintenance manuals. The supply system routed forgings, castings, magnetos, and supercharger parts through a network of subcontractors with inspection schedules embedded at each transfer point. The objective was to minimize rework and scrappage by imposing interchangeability standards that would allow parts from multiple vendors to meet a common gauge. The radar program's planning logic combined coverage geometry with production realities. Chain home sites were sited to maximize line of sight to probable approach corridors, with telephone trunk lines and power supply redundancy built into civil works. To extend capability to low-level targets and night interception, research groups planned centimetric sets that required cavity magnetrons and precision waveguide components. Production schedules sequenced laboratory prototypes into pilot runs and then into series manufacture, with specified test procedures for transmitter power, receiver sensitivity, and lobe switching accuracy. Naval requirements for gunnery and surface search sets were slotted into refit windows of cruisers and destroyers, demanding close coordination between admiralty planners, dockyards, and electronics contractors. Allied coordination reshaped British goals from late 1940. The Destroyers for Bases Agreement provided 50 U.S. destroyers in September 1940, and planning staffs integrated them into escort groups after refits. The British Commonwealth Air Training Plan, agreed in December 1939 with Canada, Australia, and New Zealand, established output targets for pilots, observers, and gunners to feed British and Dominion squadrons. This allowed the United Kingdom to concentrate more factory space on engines, airframes, and instruments rather than expanding training airfields at home. Lend-Lease, enacted in March 1941, added a financial and legal framework for American production to support British and, later, Soviet needs. British planners created allocation boards to decide which items would be made domestically, which would be procured in North America, and how to route them through convoy cycles without overloading any single port. Preparations produced miscalculations. Early reliance on ASDIC led to underestimation of night surface attacks by submarines, and the need for long-endurance escorts with improved radar and HF/DF. In aircraft production, optimistic schedules for airframe output sometimes ignored the slower expansion of foundry capacity for crankcases and superchargers, creating temporary surpluses of wings without matching engines. In shipping, risk models initially priced the Mediterranean route as intermittently usable. Italian entry into the war and Axis air strength in the Central Basin forced more traffic around the Cape, lengthening turnaround times and increasing escort hours per imported ton. The Far East Plan assumed that a European fleet unit could reinforce Singapore in crisis. Events in 1941 would test that assumption. Propaganda and information policy served planning by shaping labor supply and public behavior. The Ministry of Information framed campaigns around salvage of aluminum and steel, adherence to rationing, and acceptance of evacuation and blackout measures to reduce strain on civil defense and transport. Employers and unions negotiated dilution to widen the pool of workers qualified for precision tasks under inspection, strengthening the ability to meet schedules without breaching craft standards. Comparable efforts existed on the other side. German messaging emphasized U-boat successes to support recruiting and home front resilience, while Italian communications highlighted Mediterranean interdiction. Both influenced British threat assessments and convoy priorities. Supply lines were formalized into routings with defined escort compositions. North Atlantic convoys from Halifax and later from Newfoundland were assigned groups mixing destroyers, sloops, and corvettes, with reliefs near established support points such as Iceland. West African routes to Freetown and around the Cape supported fuel and ore imports and the outward movement of manufactured goods to Middle East bases. Within Britain, pipelines and inland tank farms reduced coastal exposure for aviation spirit, and rail schedules moved engines and airframes from Midlands factories to selected ports under dispersal and camouflage policies. Each step from forge to front line was timed against convoy sailings and dock availability. On the comparative side, British targets emphasized breadth, escorts, radar, engines, merchant shipping management, while German and Italian objectives sought concentration, submarine mass, air mining, and choke points in the Mediterranean. The United States, still neutral in 1940, increased naval patrols in the Western Atlantic and prepared industry for larger orders. Canada expanded shipbuilding and aircraft assembly for both domestic and British contracts. The Soviet Union, a future recipient of Allied material, was not yet integrated into British supply planning, but British staff studies considered potential commitments of aircraft, vehicles, and communications equipment should geopolitical conditions change. By mid-1941, the planning framework produced measurable shifts. Escort numbers were rising through emergency programs and transfers. Radar coverage thickened with improved sets in development, and engine output trended upward within known bottlenecks. Britain's role as a supplier was being codified in agreements and shipping plans that connected factories to Allied demands across multiple fronts. The period strategies were not static. They were iterative systems that recalibrated routes, tooling, and priorities against losses, scientific advances, and alliance decisions, setting the conditions for the first major clashes of capacity and countermeasure that followed. The first direct tests of Britain's industrial and organizational choices arrived across multiple theaters between late 1939 and mid-1941. At sea, convoy cycles began under hostile contact within weeks. The sinking of the liner Athenia on September 3, 1939, signaled that individual sailings would be vulnerable, but the escorted convoy, HX-1, sailed on 16 September and completed passage with its assigned force, confirming the premise that group protection could work when escorts were available. In October 1939, the German submarine arm shifted toward group tactics on the North Atlantic lanes. Attacks on early slow convoys such as SC routes exposed thin escort screens, and the need for long-endurance vessels with reliable ASDIC, depth-charge throwers, and improved command procedures. British escort groups reported contact rates that strained endurance, and refit queues lengthened as older destroyers returned to yards for sonar upgrades and light anti-aircraft additions. German commanders recorded that night surface approaches at low profile, complicated ASDIC detection, and outpaced the turning circles of escorts, reinforcing their advocacy for coordinated attacks by several boats. Norway in April to June 1940 tested dockyard repair capacity, mine-laying, and destroyer availability. The Royal Navy committed cruisers, destroyers, and carriers to transports and fire support. German forces landed by sea and air to seize ports and airfields. At Narvik in April, destroyer actions and the loss of German supply ships reduced German local naval strength, while British forces lost and damaged several destroyers in mountain-enclosed waters. The sinking of the carrier. Glorious with destroyer escorts on June 8th, removed aircraft and trained personnel at a point when naval air power was under expansion. British yards rerouted plate, turbines, and armament to repair and replacement lists. German yards faced accelerated work on destroyers and U-boats to recover fleet balance. The campaign ended with evacuations and the loss of Norwegian bases to Germany, altering convoy geometry in the North Sea, and raising the value of Iceland and the Faroe Islands as support points. The collapse of France in May-June 1940 imposed immediate logistics changes. Operation Dynamo evacuated approximately 338,000 personnel from Dunkirk between 26 May and 4 June, using destroyers, trawlers, and requisition craft under air and artillery threat. The shift from supplying an expeditionary force in France to defending the British Isles and sustaining overseas garrisons reallocated tonnage, escorts, and port labor. Channel ports lost to German control redirected shipping to western harbors. Rail networks inland adjusted to move food, coal, and imported ores around regions damaged by air attack. German plans redirected a large air force to attack British docks, storage facilities, and industrial districts to degrade ship repair and engine output. Coastal Command faced an expanded reconnaissance and anti-shipping requirement in home waters. Air combat over Britain in the summer and autumn of 1940 evaluated the integrated radar and control system tied to fighter squadrons and standardized engines. Chain home stations fed tracks into filter rooms and sector operations, allowing controllers to call up Hurricanes and Spitfires with Merlins matched to altitude bands and propeller settings derived from performance tests. On 15 August, large multi-directional raids from Luftflotten operating from Norway and France met concentrated interceptions because radar and observer corps posts established timing and altitude cues. Luftwaffe units recorded that coherent interceptions reduced bomber survival on daylight missions, which led to tactical changes, higher escort ratios, probing of low-level routes, and an eventual shift to night bombing from September. British fighter units reported high engine change and repair rates corresponding to sustained scramble cycles. Maintenance command adjusted overhaul intervals by mark to preserve reliability. German crews noted the increasing prevalence of ground-controlled interception, coordinated with searchlights and, later, airborne interception sets under trial. The Blitz from September 1940 to May 1941 imposed civilian casualties and disrupted factories, docks, and rail yards. Raids on London repeatedly hit docklands and warehouses. Coventry on the 14th to 15th of November 1940 experienced widespread damage to machine tool and automotive plants, including facilities feeding aero-engines and vehicle components. Rolls-Royce, Bristol, and de Havilland dispersed sub-assembly work to shadow sites and smaller shops. Jig and tool duplication increased resilience at the cost of additional inspection and transport complexity. German planning aimed to degrade productivity and morale. British administration prioritized rapid utility restoration, fire watching, and plant dispersal. The civil defense system reported casualties and dislocation. Production ministries tracked output dips and recovery times to adjust buffer stocks of engines, magnetos, and instruments. In the Atlantic, convoy battles in October 1940 highlighted gaps in escort density and sensor coverage. SC-7, a slow convoy, suffered heavy losses when a Wolfpack exploited night surface attacks beyond effective ASDIC range. HX-79 in the same period also lost multiple ships under coordinated submarine control. British responses combined immediate tactics, stronger close screens, support groups that could be vectored by high-frequency direction finding, with medium-term programs, more Flower-class corvettes entering service, Hunt-class and fleet destroyers completing, and radar fits on escorts to detect surfaced attackers in poor visibility. German records from this period noted the effectiveness of group tactics when air cover and escort radar were limited, and the strain of longer patrols as Allied routing diversified and winter weather reduced attack opportunities. Italy's entry into the war on June 10, 1940, shifted pressure to the Mediterranean. British routing recalculated Suez-bound traffic under submarine, torpedo boat, and bomber threat. Malta became a forward base and a target, affecting convoy scheduling and the distribution of escorts between Atlantic and Mediterranean commitments. The Royal Navy used carriers to strike at anchored units and port facilities, as at Taranto on November 11, 1940, altering the risk calculus for capital ships in confined waters. Italian and German air units increased interdiction of convoys to Greece and North Africa, compelling British planners to add anti-aircraft weaponry to escorts and to adjust cargo composition toward critical spares and fuel. The changing balance in the Central Basin elongated Cape routes and increased escort hours per imported ton to Britain. Britain's supplier role emerged in early deliveries despite attrition. Aircraft, engines, and vehicles moved to the Middle East and to Commonwealth forces. Transfers also reached Allied navies in the form of mine-sweeping gear, sonar sets, and radios. The Destroyers for Bases Agreement in September 1940 added 50 U.S. destroyers requiring refit to British standards before joining escort groups. Canadian yards launched corvettes and minesweepers for North Atlantic work. Canadian factories assembled Hurricanes to British specifications. German and Italian assessments tracked these additions, noting the proliferation of small escorts and the extension of repair and refit capacity across the Atlantic, which complicated their commerce war goals. Unexpected outcomes shaped subsequent procurement. The survivability of the integrated radar fighter system under heavy daylight pressure encouraged further investment in centimetric research and night fighter equipment. Losses in slow convoys highlighted the need for endurance, improved command arrangements at sea, and convoy rescue vessels. Damage in industrial cities required deeper dispersal of engine subassemblies and more rigorous interchangeability, so that a propeller or supercharger from one plant could fit engines built elsewhere without rework. On the Axis side, early convoy successes validated group tactics and air mining, but also revealed limits when escorts with radar and HFDF concentrated. The expansion goals for submarine numbers were retained, and training pipelines were adjusted to increase operational crews. By mid-1941, the first exchanges had clarified the parameters of the contest. Britain could preserve core import flows under convoy, but at the cost of heavy escort usage and rising ship losses in specific periods. The radar-based air defense system could keep fighter strength effective in daylight, but required rapid engine support and a growing night fighting capability. Industrial dispersal reduced single-raid vulnerability, but introduced coordination burdens that had to be managed through inspection standards and transport scheduling. These engagements provided data for redesign, escort classes with better seakeeping and electronics, aero-engines with standardized accessories and maintenance intervals, and radar with improved detection of surface submarines. The clash had begun as a contest of attrition and adaptation in which manufacturing cadence, shipping cycles, and scientific iteration were as consequential as tactical skill. Escalation. In 1941 to 1942, it forced Britain to stretch the mechanisms it had built for convoys, radar, and aero-engines while meeting new Allied commitments. In May 1941, the Ministry of War Transport consolidated shipping control and inland movement, formalizing convoy cycles and port allocations under a unified authority. Western approaches. Command refined escort group structures and began experimenting with support groups that could be detached to reinforce convoys under attack. The sinking of Bismarck on 27 May removed a surface threat, but did not reduce submarine pressure. German planners concentrated on expanding ocean-going U-boat numbers and exploiting night surface attacks coordinated by experienced commanders. From August 1941, the first Arctic convoy, codenamed Dervish, reached northern Soviet ports with aircraft and stores, opening a new route that required special winterization, ice pilots, and escorts configured for high-latitude weather. Britain's radar program entered a new phase with centimetric sets derived from cavity magnetron research. Shipborne types fitted to escorts from late 1941 allowed detection of a surfaced submarine's conning tower and periscope at shorter wavelengths than earlier metric sets, improving contact rates and poor visibility. Coastal Command installed air-to-surface vessel radar to locate U-boats at night or in cloud. Operational squadrons added searchlights mounted in aircraft to illuminate targets at low altitude over the sea, creating a combined radar visual attack method that changed night tactics. Production required precision copper, ceramic, and waveguide components, so electronics firms scaled cleanroom practices and valve manufacture, while inspection branches introduced standardized acceptance tests for transmitter power and receiver sensitivity. Aero-engine policy shifted from single-stage superchargers to higher altitude and higher boost configurations to sustain interceptor and intruder operations. Rolls-Royce increased Merlin variants with uprated superchargers and, in partnership with licensed manufacturer in North America, prepared patterns and gauges that enabled Packard to build engines to common standards. Bristol expanded sleeve valve radial production for medium bombers and coastal aircraft, while Napier resolved teething problems on high-output engines intended for fast fighters and attack types. The Ministry of Aircraft Production emphasized accessory standardization, magnetos, carburetors, and propeller governors, so that maintenance units could swap items across marques without bespoke adjustments. Training commands expanded engine handling courses to reduce premature wear from incorrect boost and mixture settings during scramble cycles. The entry of the United States into the war in December 1941 altered both risk and capacity. Routing in the Western Atlantic extended to new assembly points and required coordination with U.S. Navy and Coast Guard commands. Early 1942 saw heavy losses off the North American seaboard when coastal convoying lagged behind submarine deployment, a crisis that affected Britain because the same tankers and freighters fed British import programs and outbound military cargoes. British and Canadian escort production continued, corvettes, new sloops, and the first frigates with improved endurance and sonar stability, while the United States began mass production of standard hulls and escort carriers that would later change the balance. Planning staffs integrated these flows into port and repair schedules, accepting that 1942 would be a year of elevated sinkings while longer-range aircraft and additional escorts came into service. Arctic convoy operations escalated deliveries to the Soviet Union. Convoy cycles designated PQ outbound and QP homebound navigated seasonal daylight extremes, ice risk, and air and surface attack from bases in northern Norway. One outbound convoy in July 1942 suffered the loss of most of its merchantmen after dispersion was ordered in the face of perceived heavy surface threats. The result reoriented doctrine toward maintaining cohesion, strengthening close escort, and assigning distant cover with clearer command relationships. Cargoes included aircraft in crates, tanks, radar components, non-ferrous metals, and explosives. The industrial implication was a packing and preservation program. Engines and instruments were sealed against salt and moisture, crates were dimensioned to ship's gear, and spares were bundled to allow immediate assembly on arrival in Arctic conditions. In the Mediterranean, convoy battles to sustain Malta and support operations in North Africa imposed parallel demands. British planners split scarce escorts between Atlantic and Mediterranean routes, added light anti-aircraft weapons to escort fits, and introduced fighter direction radar on fleet units to manage air threats over narrow seas. Italian and German air forces concentrated on interdiction near choke points, raising loss rates for critical cargoes such as aviation fuel and torpedoes. To compensate, Britain allocated more manufacturing capacity to replace radar sets, gun sights, and aircraft lost in transit, and shipped repair kits and mobile workshops so that forward bases could reconstitute equipment without waiting for factory overhauls. Civil industry faced renewed air attack through 1941 and selective raids in 1942. The dispersal policy extended to aero-engine subassemblies, with crankcases, superchargers, and cylinder blocks produced at multiple sites to reduce vulnerability to a single raid. Quality control tightened around interchangeability. Gauge room standards, limit pins, and statistical sampling were enforced so that parts from separate plants would mate without rework. Transport planners scheduled night rail movements for engines and airframes under blackout rules and established inland storage to cushion temporary port closures. Utility restoration teams used standardized power and water modules to bring damaged factories back to operation, often in partial capacity, within days rather than weeks. On the German side, the expansion of submarine training pipelines increased patrols in the North Atlantic and Caribbean in early 1942. Commanders noted that centimetric radar on escorts and aircraft complicated night surface approaches. Countermeasures included radar detectors and revised tactics. Allied high-frequency direction, finding on shore, and increasingly at sea, helped concentrate escorts on U-boat reporting positions. The tactical dialogue affected industrial priorities, more shipborne radar sets, additional long-range aircraft with radar and depth charges, and escort conversions of merchant hulls filled immediate gaps while new-build frigates and carriers were completed. Britain's supplier role widened geographically. Middle East forces received aircraft, radar, and vehicles staged around the Cape. India and East African bases absorbed communications gear and port equipment to handle transshipment to Persia for overland movement to the Soviet Union. Canada continued to launch escorts and assemble fighters under British specifications, and South African yards handled repair and minesweeping tasks that freed northern yards for Atlantic work. The coordination required a rolling stock of crated engines, propellers, and instruments sized to local assembly capability and fuel quality, with manuals adjusted for climate and maintenance skill levels in theater. Political direction tracked the crisis. War cabinets reviewed shipping losses against monthly import minima for food and industrial inputs, accepting ration reductions and consumption controls to preserve bunker fuel and convoy density. Production ministries negotiated priorities between fighter programs, coastal aircraft, and bombers, with engine allocations set by theater need and survivability data. Intelligence from code breaking and reconnaissance adjusted routing and escort plans, while loss analyses identified recurrent failure modes in machinery, armament, and communications equipment to inform redesign and refit lists. By late 1942, escalation had clarified trade-offs. Britain could maintain essential imports and expand deliveries to allies, but only by committing more escorts, fitting radar and HF/DF widely, and accepting higher ship turnaround times. Fighter and coastal aircraft output, anchored by engine standardization and shadow factory maturation, supplied home defense and overseas fronts, yet every diversion to Arctic or Mediterranean routes had to be balanced against Atlantic convoy protection. The crisis period thus fused scientific advances, industrial dispersion, and alliance logistics into a system capable of absorbing shocks, while preparing the larger force changes that would define the subsequent peak of the campaign. By 1943, the contest reached a peak in which industrial cadence and operational pressure aligned. In the North Atlantic, convoy ONS-5 in late April-early May 1943 became a test of escort doctrine and electronics. Approximately 40 merchant ships with close and support groups engaged more than 20 submarines over several days in heavy weather. The convoy lost 13 ships, but escorts employing centimetric surface search radar, HF/DF, and head-throwing mortars destroyed or fatally damaged multiple attackers and held cohesion through repeated night approaches. In the same month, Allied air and sea forces sank 41 U-boats, a loss rate that forced a German withdrawal from the mid-ocean focal area. The technical elements behind these outcomes, Type 271/272 shipborne radar on escorts, ASV Mark III on long-range aircraft, improved sonar stability in new hulls, and coordinated HF/DF fixes from shore and ships, were the product of prior investment in magnetron production, waveguide machining, and standardized fit procedures at dockyards. Escort numbers and quality reached new levels. Over 250 Flower-class corvettes were in service or completing, joined by River-class frigates designed for better endurance and seakeeping, and 78 Captain-class destroyer escorts transferred under Lend-Lease began joining the Royal Navy. Escort carriers of the Attacker and Bogue types put radar-equipped aircraft over convoys, extending protection into the former air gap. The very long-range Liberators operated first from Iceland and Northern Ireland and, after the October 1943 agreement on base rights in the Azores, from airfields that closed the Central Atlantic to routine submarine transit. Coastal Command integrated radar, HF/DF queuing, and the Lee Light into a standardized night attack sequence. Bay of Biscay transit zones became hazardous to surfaced boats as patrol lines tightened and aircraft endurance increased. Aero-engine output hit its operational stride around high altitude and long-range requirements. Merlin two-stage supercharger marks powered interceptor Spitfire 9 squadrons, and long-legged Mosquito variants used for intruder and reconnaissance roles. Packard-built Merlins, produced to British gauges, entered service in North American airframes that would escort bombers deep into occupied Europe later in the year. Bristol's Hercules radials sustained coastal command and medium bomber fleets with reliability at maritime altitudes, while Griffin-powered naval fighters began to appear on the fleet and escort carriers. Production discipline emphasized accessory interchangeability and test cell throughput. Magnetos, supercharger casings, and propeller governors were pooled across plants, and hour-limit overhaul cycles were tuned by Mark to minimize premature removals while sustaining scramble readiness. Training units adjusted procedures to reduce engine wear from overboosting during combat climbs, a small change with measurable effect on availability. Radar left the laboratory phase entirely. Chain home and low-level extensions maintained the home air picture. Centimetric sets migrated to ships and aircraft in volume. Gunnery radars improved naval fire control and poor visibility, and at night, altering the odds in cruiser and destroyer actions that escorted Arctic convoys. Airborne interception equipment matured to the point that night fighter units could be tasked against defined bomber streams, releasing other formations to maritime patrol. The industrial footprint behind this capability included multiple valve and magnetron lines, strict acceptance testing for transmitter power and receiver noise, and a trained maintenance cadre able to swap standardized modules rather than diagnose to component level under field conditions. The Arctic route reached its own crest. JW and RA convoy series maintained deliveries of aircraft in crates, vehicles, radar sets, and explosives to northern Soviet ports through seasons of continuous daylight or darkness, ice risk, and proximity to Axis bases. Escort groups combined British, Canadian, and later U.S. units with cruiser and battleship cover. On the 26th of December, 1943, the covering force for JW-55B located and engaged the German battlecruiser Scharnhorst north of North Cape. Radar-directed gunnery and destroyer torpedo attacks sank the ship, with 36 survivors from a crew of roughly 1,900. The action removed a major surface threat to the route and demonstrated the integration of centimetric sets, fighter direction, and heavy unit tactics. German records noted the difficulty of night operations against radar-equipped opponents in high seas, reinforcing the shift toward avoiding decisive surface action in the far north. Britain's role as supplier broadened with major amphibious and Mediterranean operations. Torch, November 1942, had already drawn on British escorts, carriers, and radar units. The 1943 campaigns in Tunisia, Sicily, July, and mainland Italy from September required continuous flows of landing craft, radio sets, vehicles, and aircraft staged via the western approaches, Gibraltar, and Suez lines. Escort allocations balanced Atlantic convoy protection against narrow sea threats where air attack density was higher. Fighter direction radar on fleet units and ground-controlled interception at forward airfields, coordinated with carrier and shore-based squadrons. Italian and German air forces prioritized fuel and ammunition ships. British planners responded by adjusting cargo composition, adding light anti-aircraft armament to more escorts, and forward positioning mobile repair parties so that damaged radar, gun sights, or engines could be returned to service without a factory overhaul. Civil and industrial pressures at the peak were continuous rather than episodic, while the intensity of area bombing against British cities was lower than in the 1940 to 1941 Blitz. Selective raids and flying bomb preparations later, 1943, required dispersal and rapid repair capacity. Engine sub-assemblies, crankcases, cylinder blocks, and superchargers were built in parallel lines at shadow sites with common gauges. Dockyards duplicated radar test gear and alignment fixtures to reduce turnaround on refits. Rail and road transport synchronized to convoy cycles, moving engines and airframes from Midlands factories to Western ports under blackout and camouflage protocols. Fuel boards managed allocations of aviation spirit and naval bunker fuel, with inland storage and pipeline links to reduce coastal exposure and shorten port times. Axis countermeasures and adaptations were integral to the peak. U-boats deployed radar warning receivers to detect Allied centimetric sets and experimented with revised approach patterns. Additional anti-aircraft armament was mounted on some boats for Bay of Biscay transits. Training output increased, but the experience level of new crews declined as losses mounted. In the Mediterranean, Italian and German staffs pushed reconnaissance and air mining at straits and harbor entrances. Surface torpedo craft exploited night and coastal clutter. These measures produced local successes and forced Allied adjustments, such as more widespread shipborne radar fits, convoy route variation, and the commitment of escort carriers to threatened sectors. Quantitatively, the balance shifted but remained contingent on sustained production. Merchant tonnage losses fell after mid-1943 as escorts, radar, HF/DF, and long-range air cover multiplied, yet import targets still required dense convoy schedules and disciplined port turnaround. The Royal Navy and Royal Canadian Navy fielded larger, more specialized escort groups with common drills. Coastal Command logged more flying hours over critical lanes with radar-equipped aircraft. Engine deliveries supported home defense and overseas commitments simultaneously, but this depended on interchangeability and trained maintenance rather than airframe counts alone. Britain's capacity at the peak thus combined three mutually reinforcing elements: electronics that extended detection and control into night and weather, hulls and aircraft optimized for endurance and seakeeping, and engine plants whose standardized accessories and test regimes kept squadrons and escorts available for the sustained operations that defined 1943. Adaptation in 1943 to 1944 unfolded as a series of engineering, organizational, and tactical adjustments designed to preserve convoy flow, extend detection into night and poor weather, and keep aircraft serviceable at high sortie rates while meeting Allied demands. In the Atlantic, German submarines introduced acoustic homing torpedoes against escorts and increased night surface approaches until centimetric radar and HF/DF compressed their maneuver space. British and Commonwealth groups countered with towed acoustic decoys on escorts, standardized radar fits that detected low-profile targets in sea clutter, and ahead, throwing mortars that attacked without losing contact. Escort doctrine consolidated around composite groups mixing frigates with long endurance, destroyers for sprint and gunfire, and corvettes as close screen, supported by escort carriers whose radar-equipped aircraft denied submarines the surface. Shore-based direction centers fused HF/DF bearings from multiple stations to generate intercept vectors. This process, once experimental, became routine signal flow with established priorities for relays and plain language brevity codes when secure channels were saturated. Submarine snorkels appeared in larger numbers from late 1943, reducing radar exposure but limiting speed and situational awareness. Coastal Command expanded radar altitudes and search patterns to exploit wakes and exhaust plumes at periscope depth. Aircraft crews adopted tactics that combined radar cues with timed visual runs during moonlight or with artificial illumination when possible. On the industrial side, radar manufacturers increased cavity magnetron output with tighter tolerance control on resonant cavities, and introduced modular receiver units so that squadron fitters could swap entire sub-assemblies on the flight line. Maintenance Command codified radar servicing intervals by set and platform, reducing no-fault removals and conserving spare modules for high-intensity sectors. Aero-engines underwent parallel adaptation. Fighter units transitioned in quantity to Merlin, two-stage marks for high-altitude interception, and to Griffin-powered naval variants for carrier operations. Coastal squadrons retained Hercules radials valued for reliability over water. Packard-built Merlins, produced to British gauges, entered service alongside domestic engines with accessory standardization, magnetos, carburetors, and propeller governors that allowed maintenance units to draw from mixed pools without custom shimming. Napier resolved serviceability bottlenecks on high-output engines used in fighter-bomber roles by revising cooling and sleeve timing tolerances, changes that were reflected in new test cell procedures and acceptance limits. Overhaul policy shifted from calendar-based to hour and condition regimes, borescope inspections, oil analysis where facilities existed, and standardized ground runs reduced premature removals that had consumed capacity during earlier intensive periods. The air defense system adapted to new weapons. Beginning in June 1944, pilotless aircraft launched against southern England required rapid realignment of radar plotting, anti-aircraft belts, and fighter tasking. Controllers layered gun zones with proximity-fused ammunition near the coast, established fighter interception boxes further inland, and used radar to time sector handoffs to minimize dead space. Fighter Command tasked high-performance types to fast, low-altitude targets. Jet aircraft entered limited service for point defense under ground control. When ballistic missiles began arriving in September, only civil defense, deception of aim points, and offensive action against launch areas could mitigate effects. Nevertheless, radar tracking and impact plotting, improved warning and rescue response times, and industrial dispersal limited the duration of factory stoppages. Resource management deepened as shipping and labor remained binding constraints. The Ministry of War Transport coordinated tanker cycles with inland pipeline networks feeding airfields and naval bases, while the Ministry of Fuel and Power balanced industrial coal allocations against domestic consumption. Compulsory recruitment to mines increased output, but required training and safety programs that affected schedules. Utility schemes standardized furniture and clothing to cut non-essential manufacturing and release machine tools and transport to priority sectors. In factories, dilution agreements widened the pool of workers eligible for precision tasks under inspection. Women staffed electrical, instrument, and gauge room work at scale, and technical colleges delivered short courses aligned to factory needs, waveguide measurement for radar plants, gauge reading for engine shops, and vibration analysis for propeller overhaul lines. Absenteeism spikes during flying bomb periods were managed with staggered shifts, on-site canteens, and shelter provisions integrated into production layouts. Supplying allies required tailored adaptations. For the Soviet Union, Arctic convoys continued with escorts equipped for high-latitude radar and gunnery in darkness and poor weather, while the Persian corridor moved vehicles, radios, and machine tools through rail and road links that demanded standardized crating and climate-proof packing. North African and Italian campaigns consumed radar sets, engines, and landing craft components staged via Gibraltar and Suez. Forward repair parties carried alignment tools for radar and calibration kits for propellers, so that equipment could return to service without a full factory overhaul. Preparations for cross-channel operations required new engineering solutions. Prefabricated harbor units demanded controlled delivery of steel, tugs, and towing gear. Undersea pipelines called for exacting pump specifications and corrosion allowances to move aviation spirit and motor fuel to continental depots. Each innovation implied a bill of materials that production ministries had to reconcile with ongoing escort, engine, and radar commitments. German and Italian adaptations elicited further British change. Submarines fitted radar warning receivers and improved hydrophone installations. British escorts responded by altering radar frequencies, reducing emissions during approach, and refining passive search with sonar sweeps at variable depths. Acoustic torpedoes forced escorts to adjust speeds and employ decoys. Revised convoy formations decreased the likelihood that a single homing weapon would disable a key escort. In the Mediterranean and Adriatic, small surface craft intensified night attacks under coastal clutter. British countermeasures combined shore-based radar, light forces with fast radar-directed guns, and aircraft night patrols directed by ground and ship plots. After Italy's armistice, the redistribution of Axis naval pressure changed convoy risk calculations, allowing more escorts to shift to the Atlantic and northern routes, while co-belligerent Italian facilities took on repair tasks that shortened turnaround for Allied units. Adaptation also meant revising measurement. Statistical control moved beyond monthly tallies to machine-hour utilization, scrap rates by component type, and radar mean time between failure by environment. Dockyards tracked refit durations against standardized task lists for radar and sonar installations. Deviations triggered engineering reviews that either simplified fit procedures or revised drawings. In engine plants, gauge room audits reduced out-of-tolerance drift. Interchangeable subassemblies increased first-time fit rates at maintenance units. These incremental changes yielded availability gains. Escort groups met more sailing dates without substitutions, and fighter and coastal squadrons reported higher in-commission rates despite intense tasking. Psychological and organizational pressures were continual. Civil defense and industrial security integrated with production schedules so that restoration teams and spare power units were prepositioned for rapid response. Information ministries emphasized salvage, ration adherence, and workplace safety, not as morale narratives but as mechanisms to sustain throughput. Comparable dynamics existed on the opposing side. Submarine crews trained on new devices under compressed timelines. Ground crews for night and coastal aircraft faced overload as losses mounted. Electronics workshops struggled with scarce materials for counter-radar equipment. Each coalition balanced claims and setbacks with adjustments to training syllabi, maintenance regimes, and replacement planning. By late 1944, resistance and adaptation had a cumulative effect. In the Atlantic, convoy protection combined radar, HFDF, long-range aircraft, and standardized escort tactics to reduce sinkings and raise submarine loss rates in contested zones. Snorkel-equipped boats survived more patrols, but found fewer profitable engagements. Over the United Kingdom, integrated radar plotting, anti-aircraft belts using proximity fuses, and fighter interception reduced successful pilotless aircraft strikes, as controllers learned the speed profiles and routes most commonly used. In factories and dockyards, interchangeability and modular servicing shortened refits and overhauls. Britain could now sustain home defense, support multiple overseas operations, and deliver significant quantities of engines, radar sets, and naval equipment to allies, not through a single breakthrough, but through continuous adjustments in technology, training, and process control that converted industrial potential into operational endurance. The turning point emerged between May 1943 and summer 1944, when cumulative measures in convoy protection, radar, and aero-engines shifted outcomes from preservation of minimum import tonnage to sustained expansion for joint operations. In the Atlantic, the concentrated engagements around convoy ONS-5 from 29th April to 6th May 1943 and subsequent patrol losses forced the German submarine arm to curtail mid-ocean Wolfpack activity. During May, 41 submarines were sunk by air, and sea forces employing centimetric radar, HF/DF, and coordinated support groups. British, Canadian, and U.S. escorts now operated with common procedures and interchangeable electronics. Very long-range aircraft with ASV radar covered former gaps from bases in Iceland, Northern Ireland, and, after October 1943, the Azores under a basing agreement. German records from the period cited radar detection and air coverage as the decisive environmental change, and training directives shifted towards snorkel use, radar warning receivers, and revised approach profiles. The net effect was a measurable decline in merchant losses per convoy sailed and a rise in submarine losses per patrol, altering the cost calculus for both sides. Industrial signals matched the operational inflection. Escort carriers of bogue and attacker types, river-class frigates with improved endurance, and standardized corvettes reached the western approaches in numbers that enabled rotation without stripping one route to cover another. Coastal Command integrated ASV, Mark III radar with Lee-Light procedures, producing repeatable night attack sequences that crews could execute after short conversion courses. On-shore, electronics firms had stabilized magnetron dimensions and acceptance tests so that shipyards and squadrons received radar sets with predictable maintenance intervals. In engine plants, two-stage Merlin marks and Hercules radials reached acceptance rates that allowed a steady flow to frontline and training units while maintaining overhaul reserves. Packard production to British gauges increased the pool without introducing incompatible accessories, allowing maintenance command to allocate engines to units by operational profile rather than by manufacturer. Allied logistics realigned on the assumption that convoy loss rates would remain within planned margins. War cabinet committees translated the new loss ratios into higher import targets for food, petroleum, and non-ferrous metals, while reserving shipping space for outbound military cargo. The Arctic route continued under JW and RA cycles with cruiser battleship cover. The sinking of Scharnhorst during JW55B on 26 December 1943 removed a surface threat to the northern corridor. In the Mediterranean, the September 1943 Italian armistice reduced Axis naval pressure on central routes, enabling redistribution of escorts to Atlantic and Arctic commitments, while co-belligerent Italian facilities contributed repair capacity under Allied supervision. German and Japanese planning remained oriented on submarine warfare, but the deployment of escort carriers and longer-range aircraft created transit zones where surface movement was increasingly hazardous, as reflected in patrol logs and plotted sighting densities. The turning point also consisted of decisions on how to convert regained shipping security into offensive capability. British industry, operating with tighter interchangeability in engines and standardized radar fits, could schedule deliveries for large amphibious operations while sustaining home defense and overseas garrisons. Preparations for a cross-channel assault required specialized components, landing craft, beach clearance gear, radio nets compatible across services, and portable navigation and fighter direction radars. Prefabricated harbor units were planned with bills of material that drew steel, tugs, and towing gear from yards already producing escorts. Allocation boards sequenced these demands to prevent idle berths or shortages of critical forgings. Undersea pipeline projects specified pump output, pipe wall allowances, and corrosion control to move fuel from British depots to continental distribution points, reducing tanker exposure in the channel once lodgements existed. Opposing adaptations continued, but no longer produced the same aggregate effect. Submarines fitted snorkels to lower radar exposure, yet operating submerged at low speed reduced tactical flexibility and situational awareness. Radar warning receivers increased evasion in some cases, but escorts and aircraft altered frequencies and employed passive tactics to mask approaches. Acoustic homing torpedoes required procedural countermeasures, towed decoys, speed changes, and coordinated turns that were incorporated into convoy drill books and practiced at sea. In night and bad weather conditions near the Bay of Biscay, radar-equipped aircraft forced U-boats either to remain submerged for extended periods or to attempt transits under constant threat. Both choices reduced patrol endurance and contact opportunities. The balance did not eliminate submarine successes, but it confined them within loss rates that no longer degraded convoy throughput below planning minima. By early 1944, Britain's role as a supplier had moved beyond emergency redistribution to planned surpluses for specific theaters. Engine deliveries supported fighter defense of the United Kingdom, long-range maritime patrols, and tactical air forces preparing for operations in Italy and Northwest Europe. Radar sets were available in series sufficient to equip escorts, coastal aircraft, and ground-controlled interception posts on both sides of the channel. Naval construction maintained escort output while providing the aviation facilities that would accompany assault convoys. Training pipelines, pilots under the Commonwealth Plan, radar mechanics from technical schools, and marine engineers from accelerated courses met intake targets with attrition allowances derived from 1943 data, rather than the higher contingencies used in 1941 to 1942. The strategic consequence appeared in the ability to synchronize multiple fronts. In the Atlantic, convoy cycles sustained higher import targets while moving outbound vehicles, radios, and engineer stores for Mediterranean and northern operations. In the Arctic, deliveries to Soviet ports continued through winter darkness, with escorts configured for gunnery and radar in high latitudes. In the Indian Ocean and Persian corridor, vehicles and communications equipment moved on schedules aligned with rail and road capacity, supported by crating standards that matched local handling gear. Each route had distinct hazards: ice and air attack in the north, long distances and monsoon weather in the east, narrow seas and air threat in the Mediterranean. But by mid-1944, the combined escort, radar, and engine systems held loss and delay within bands that planning staffs had incorporated into timetables for larger campaigns. The turning point did not rest on a single battle or device, but on the interaction of institutions and technologies. Statistical control offices compared escort availability against convoy sailings, radar mean time between failure against patrol hours, and engine in commission rates against squadron sorties, redirecting spares and labor where variance exceeded limits. Dockyards applied standardized fit sequences for radar and sonar that cut refit durations. Engine works maintained gauge room audits that kept parts within tolerances across dispersed plants. Air and naval commands shared procedures for radar use, emission control, and attack patterns. On the other side, submarine commands compressed training timelines to reconstitute crews and sought new countermeasures. But the attrition of experienced personnel and the widening coverage of radar and air patrols limited operational payoffs. By the summer of 1944, Britain could contribute escorts, carriers, radar units, and aero-engines to continental operations without undermining convoy protection. Shipping losses persisted, but import and export tonnages met or exceeded schedules set after mid-1943. Fighter defense remained viable during new threats from pilotless and ballistic weapons, because radar plotting and engine maintenance regimes preserved sortie rates despite diversion costs. The decisive change was systemic. Detection extended into conditions that previously favored the attacker. Endurance and maintenance kept platforms available, and industrial interchangeability allowed rapid recovery from damage and wear. This combination marked the shift from survival under pressure to the capacity to support and conduct large, simultaneous operations across several theaters. Combat operations that had defined Britain's industrial tempo eased unevenly from late 1944 to mid-1945, and the institutions built for convoy, radar, and aero-engines transitioned from maximum effort to controlled drawdown. In the Atlantic, convoy schedules continued through winter, 1944 to 1945, with denser escort groups and routine very long-range air cover. Submarines operating with snorkels reduced radar exposure, but at the cost of speed and observation. Contact opportunities fell as escorts and aircraft refined passive tactics and HF/DF queuing. In early May 1945, orders to cease hostilities and surface for surrender ended organized U-boat operations. Boats proceeded under guard to Allied ports, while others were scuttled at sea or later disposed of in controlled sinkings. Escort groups remained on station while capitulations were verified, and minesweeping units reopened approaches to major harbors. The statistical effect appeared quickly. Convoy losses dropped to isolated incidents from residual mines and derelicts, and port turnarounds shortened as air threat receded, and repair resources were reassigned from damage control to backlogged maintenance. In northern waters, the last Arctic convoys completed their deliveries in spring 1945 with heavy cover, but fewer attacks as German surface and air units withdrew or surrendered. The capture or evacuation of Norwegian bases removed staging points that had threatened the route since 1941. Escort doctrine, now standardized across British, Canadian, and U.S. units, shifted from intensive defense to supervision of surrenders, repatriation voyages, and clearance of minefields along traffic lanes to Murmansk, Archangel, and the Barents approaches. Operational focus turned from protecting specialized cargo, crated aircraft, engines, radar, to returning empty tonnage for redeployment and carrying relief supplies to ports where handling gear and labor had been degraded by occupation and winter conditions. In the Mediterranean, Italy's armistice and the advance up the peninsula had already reduced the density of Axis interdiction by late 1943. In 1945, convoy work centered on sustaining forces in Italy, supporting operations in the Adriatic and Aegean, and then shifting capacity to repatriation and relief. Escort carriers and destroyers repurposed aircraft and radar detachments for anti-mine patrols, navigation assistance, and air-sea rescue. Greek islands and Balkan coasts required hydrographic resurvey after years of neglected buoyage and the laying of defensive fields. Radar and communications equipment originally fitted for combat now underpinned traffic control, approach beacons, and coastal reporting nets that enabled merchant traffic to resume under civil authority. Over the British Isles, air defense networks remained active to the end of the European War to counter pilotless and ballistic weapons, then reoriented toward air traffic control, meteorological plotting, and training once threats ceased. Chain home and low-level radar sites entered caretaker status. Airborne interception units wound down as night raids stopped. Fighter and coastal squadrons converted to transport, reconnaissance, and communication roles aligned with demobilization, repatriation of prisoners of war, and redeployment toward the Far East until Japan's capitulation. Engine maintenance organizations reduced scramble-driven overhaul tempos, but kept test cells active for transport and maritime aircraft operating long sectors over water. Civil aviation planners began adapting surplus airframes and ground equipment to emerging routes, using radar practices refined in war for peacetime navigation and approach control. Industrial production entered a managed contraction rather than an immediate halt. The Ministry of Aircraft Production and Admiralty supply branches canceled or deferred contracts for airframes and escorts not yet on the line, completed those near finish, and redirected labor and machine tools toward repair, overhaul, and essential civil work. Shadow factories that had produced Merlin and Hercules components continued output for replacements and spares, while engineering staff mapped conversion paths to civilian goods or transport equipment. Gauge room standards and interchangeability, imposed to sustain wartime throughput, eased reconversion by allowing existing tools and fixtures to switch to standardized civil parts without full rejigging. Electronics plants, having stabilized magnetron and valve series, fulfilled final service orders while preparing to support coastal navigation, lighthouse beacons, and harbor radar for shipping control. Shipping and port administration faced immediate humanitarian tasks. Minesweeping flotillas cleared approaches to British, Dutch, Belgian, and German ports. Merchant vessels carried food and medical supplies to liberated areas where rail and inland waterway capacity had been damaged. In the Netherlands, famine relief in spring 1945 combined airdrops with coastal shipments once mine clearance allowed. In Greece and parts of Italy, cargoes prioritized grain, fuel, and medical stores to stabilize urban populations and enable port labor to return in numbers sufficient for sustained throughput. The Ministry of War Transport integrated relief sailings into convoy cycles where hazards persisted and then progressively relaxed convoying as routes were certified open. Tankers redistributed fuel stocks to reconstruction priorities, while inland pipelines and storage that had protected aviation spirit and naval bunker fuel now supported civil electricity and transport recovery. For the armed services, withdrawal meant demobilization schedules and ship decommissioning layered onto ongoing commitments. The Royal Navy retained groups for occupation duties, Pacific operations, and mine clearance, while older escorts entered reserve or disposal. Dockyards shifted from emergency refits to planned maintenance and conversion tasks. Some Flower-class corvettes and River-class frigates were reconfigured for peacetime roles, such as fisheries protection, or transferred abroad under post-war agreements. Air commands reduced fighter and coastal establishments in stages, released crews and ground staff under age and service schemes, and concentrated remaining technical cadres in units supporting transport and survey work. Training pipelines contracted but did not collapse. Specialized skills, radar technicians, engine fitters, navigators, were required for residual tasks that could not be handed off immediately to civilian agencies. Immediate consequences were uneven across sectors. Merchant shipping had suffered cumulative losses over 6 years. New wartime builds and foreign charters kept essential tonnage afloat, but repair backlogs and fatigue in older hulls required dock time, even as peacetime demand for carriage rose. Civilian rationing remained in force, reflecting both the lag in agricultural and import recovery and the need to manage foreign exchange during the transition from lend-lease financing to post-war arrangements. Labor markets absorbed returning service personnel, while factories determined which skilled wartime roles translated into peacetime production. Electrical, instrument, and machine tool experience found ready application in transport, power, and consumer goods sectors, while heavy shipyards navigated a slower shift as naval orders declined before merchant replacements ramped fully. Comparative outcomes across coalitions highlighted different withdrawal trajectories. German naval and air establishments contracted under surrender terms, with surviving submarines and surface units gathered for disposal. Electronics and engine plants stood idle or operated under Allied supervision, pending decisions on dismantling or conversion. Co-belligerent Italian facilities resumed civil repair and construction under constraints set by armistice agreements. Soviet ports received final Allied convoys and then reverted to domestic traffic and reparations shipments. Allied radar detachments and signals parties withdrew as local control reasserted. North American yards and factories tapered military production later than Britain because of Pacific commitments, but began canceling Atlantic-focused programs in mid-1945. Joint escort doctrine and radar standards nonetheless persisted in training syllabi and manuals that informed post-war naval practice. Humanitarian and security contingencies continued to draw on wartime systems during withdrawal. Port radar, convoy signaling procedures, and standardized radio nets enabled the movement of displaced persons, the return of prisoners of war, and the delivery of relief with fewer collisions and delays than would have been likely without those controls. Minesweeping and hydrographic survey remained dangerous, with casualties recorded from contact with modern influence mines and unexploded ordnance. Escort groups converted to patrol and rescue roles mitigated some risks but could not eliminate them. The logistical habits of total war, statistical tracking of machine hours, stock levels, and voyage cycles, provided a managerial language for reconstruction authorities planning steel, fuel, and shipping allocations under tight resource constraints. By the end of 1945 in Europe, the withdrawal phase had rebalanced Britain's organizations from maximum-risk convoy defense and emergency industrial dispersion toward restoration of trade routes, measured demobilization, and reallocation of technical assets to relief and reconstruction. The systems that had supported naval construction, radar deployment, and aero-engine maintenance did not disappear. They were repurposed to clear mines, guide traffic, overhaul transports, and deliver supplies to regions emerging from occupation and combat damage. The immediate aftermath therefore consisted not of an abrupt stop, but of a controlled handover, in which procedures and equipment developed for survival were applied to stabilize the transition from war to a constrained peace. The long-term effects of Britain's total war organization were institutional, technological, and geopolitical. Ministries created to manage throughput, aircraft production from May 1940, war transport from May 1941, and supply left a template for central coordination that persisted in peacetime planning bodies and procurement rules. Statistical control, introduced to track machine hours, scrap rates, and convoy cycles, migrated into civil administration as routine management practice. Gauge room discipline and interchangeability standards established across shadow factories simplified post-war reconversion. The same jigs and gauges that produced Merlin and Hercules accessories supported standardized parts for rail, power generation, and civil aviation. On the maritime side, escort group structures, HF/DF networks, and radar-controlled traffic procedures were retained as the basis for post-war sea lane security and air-sea rescue, shaping doctrines later adopted by alliances that patrolled the North Atlantic and Mediterranean. Technological legacies linked laboratory work to civil infrastructure. Centimetric radar, developed through cavity magnetron production lines and modular receivers, underpinned post-war air traffic control, coastal navigation, and harbor approach beacons. Chain home sites and low-level radars were either decommissioned or adapted for meteorology, range finding, and civil aviation services. Airborne interception techniques, once focused on bomber streams, informed instrument landing aids and controlled descent procedures. In propulsion, experience with two-stage superchargers, sleeve valve cooling, and accessory standardization fed into transport engine reliability targets that prioritized long time on wing. Jet propulsion matured rapidly after 1944. The industrial habits formed around test cell throughput, accessory interchangeability, and gauging supported early jet manufacture and overhaul regimes. Naval electronics and gunnery radar progressed into marine navigation sets and coastal surveillance systems used by ports reopening to heavy traffic. Shipbuilding's wartime conversion left mixed outcomes. Emergency programs had delivered large numbers of corvettes, frigates, and escort carriers by 1943 to 1944, but these hulls were specialized for convoy speed and anti-submarine roles. Post-war merchant demand required different forms: bulk carriers, tankers, liners, at scales and speeds that pressed yards to retool beyond wartime jigs. Canadian and British yards that had produced standardized escort hulls applied modular assembly techniques to peacetime ship types. Where retooling lagged, order books contracted until designs were updated. Minesweeping and hydrographic survey, performed by ships fitted with radar and acoustic gear, remained a significant task into 1947, as routes to northern and Baltic ports were cleared of contact and influence mines. Britain's role as supplier created precedents for multinational production and training. The Commonwealth Air Training Plan, agreed in December 1939, graduated air crew who populated British, Canadian, Australian, and New Zealand units. Its campus model, syllabi, and standardized instruments set a pattern for joint training that persisted. Cross-Atlantic production arrangements, Packard-built Merlins to British gauges, Canadian-assembled fighters to British drawings, U.S.-built Captain-class destroyer escorts transferred under Lend-Lease, established shared standards that eased coalition maintenance. Reverse flows existed as well. British radar concepts, proximity fuse insights, and tactical procedures influenced American, Canadian, and Soviet practice. In return, American mass production of tankers, cargo ships, and long-range aircraft altered British routing and escort doctrine from 1943 onward. The result was a post-war baseline in which NATO navies and air forces used compatible radars, radios, and maintenance manuals derived from wartime convergence. Economic consequences were immediate and measurable. Merchant tonnage lost during 1939 to 1945 required replacement before trade could resume on pre-war schedules. Wartime builds offset a portion, but repair backlogs and hull fatigue meant extended dock time through 1946. Foreign exchange constraints shaped import priorities, a continuation of wartime treasury practice that had allocated dollars to machine tools, fuel components, and ball bearings. Debt and settlement arrangements following the end of Lend-Lease in August-September 1945 required new financial instruments. Bulk purchasing, rationing, and pipeline management remained in place while currency and shipping stabilized. Labor reallocation drew on skills gained under dilution agreements. Instrument inspectors, radar technicians, and engine fitters moved into power, transport, and consumer goods, while heavy yards adjusted more slowly as naval work tapered before merchant orders accelerated. Culturally, public memory focused on combined civil-military systems rather than single arms. Evacuation, civil defense, convoy signals, and factory dispersal were remembered as interlocking components of a national response. Memorials and commemorations included service branches and merchant seafarers whose casualty rates in certain convoy periods equaled or exceeded those of armed forces. In northern ports, convoys to Soviet destinations became part of local memory, joined by exhibits on loading gear, crating of aircraft and engines, and the harbor control rooms where radar plots and voice circuits coordinated sailings. Industrial museums preserve shadow factory fixtures, test cell instruments, and standardized gauges to document how volume and interchangeability had been achieved. Historical debates that followed were structured around comparative contribution and opportunity cost. One set of arguments weighed the relative importance of escorts, radar, and long-range aircraft in reducing convoy losses after May 1943, with datasets assigning different weights to HF/D, FQing, centimetric detection, escort carriers, and Azores basing. Another examined engine allocation between fighter, coastal, and bomber commands, asking whether early shifts in 1940 to 1941 would have changed attrition or interception rates. Analysts compared output curves for corvettes, frigates, and destroyer escorts against sinkings to test whether reinforcement or technology produced the inflection. Studies of radar emphasized integration, filter rooms, sector stations, and standardized maintenance over invention alone. Counter-arguments cited the lag between prototype and series production as a limiting factor during 1939 to 1941. On the Allied side, assessments measured British industrial capacity against American late-war mass production, tracing how British systems bought time until larger flows arrived and how British electronics and doctrine influenced the deployment of those flows. From other perspectives, German and Italian records documented adaptive cycles that intersected with British choices. Submarine commanders described the move from night surface approaches to snorkel patrols, the introduction of radar warning receivers, and the tactical constraints imposed by centimetric radar and long-range aircraft. Italian naval and air units recorded the effects of carrier strikes, fighter direction radar, and choke point convoying in narrow seas. After armistice, co-belligerent yards and crews contributed to Allied repair and mine clearance tasks. Soviet archives tied Arctic deliveries to specific operations and industrial recovery markers. They also noted the limits imposed by ice, darkness, and port handling capacity, elements that British loading plans and escort doctrine had sought to accommodate with crating standards and gunnery radar. The final balance of significance lies in systems engineering applied at national scale. Britain coordinated ministries, laboratories, and factories to deliver escorts with standardized electronics, radar networks with maintenance regimes, and aero-engines with interchangeable accessories, then linked them through convoy and air defense procedures that treated time as the decisive variable. The measurable outcomes, reduction in merchant losses after spring 1943, sustained engine availability for home defense and overseas air forces, persistent radar coverage for interception and navigation, were not ends in themselves but enablers of a coalition strategy that required secure sea lanes and reliable air operations across several theaters. The legacy endured in post-war maritime patrols, civil aviation control, industrial quality systems, and alliance logistics, where the methods first used to hold minimum tonnage and fighter readiness became the routine practices of peacetime management and collective security.